Hello everyone, we the GATE Academy people are here with another video. It is from the subject of strength of materials, and the topic is Introduction to Theories of Failure. Before going to that, let me introduce myself. My name is Jacob Prasanna Kumar. I am a faculty in the GATE Academy Private Limited. I teach the subjects of sound and machine design, and I am an alumni of IIT BHU Varanasi, so where I did both my bachelor's and master's through integrated dual degree program. Now, in this video, I will be going with the topic of Introduction to Theories of Failure. What I have observed was the concept of theories of failure is not well explained in many textbooks. Because of that, though you are actually preparing from 2 or 3 textbooks and giving the GATE questions, you would not be reaching a situation where 100% you're going to get correct answer to the particular question. So here I have simplified the explanation part so that once you complete the explanation part, or once you're understanding the basic principle on which the theories of failure are built, you can solve any question just by doing simple mathematics or following some formula. So in this one, I'm going with this introduction of theories of failure. We know that if we are having a particular material, we can find out strength. That means strength means the stress the material can take up to failure. And this failure is actually defined as yielding in ductile materials and fracture in brittle materials. So because once yielding happens in ductile materials, we can't use them. We stop using it. Once the material of which is a brittle material experiencing fracture, we'll stop it using. So we can't use a machine element once the stress in it is going beyond yield point or ultimate point. So those 2 parameters or those 2 values are taken as strength of the material. Now, when you are going with a particular strength, you can find out strength only in some loading cases. That means you take tensile loading or compression loading or shear loading. In those cases only, you can find out the strength very easily, or you can decide very easily by doing experiment that how much value of load will cause or how much value of stress will cause failure of the particular material. But if you are having a combination of loading cases, it's not actually possible. Let me explain you the earlier things, that is tensile loading. So if you are taking a tensile loading case, for example, it's a ductile material. So ductile and tension, or ductile material in tension. So here it will be correspond to yielding. So yield point I will denote it by SYT. Now second one, I can have a brittle material in tension. The dimension is SUT because fracture happens at the ultimate point, so SUT I am denoting it here. In the same way, if you are having ductile under compression, so denoted by SYC. Next one is brittle and compression. It will be SUC. In the same way, if there is ductile which is under shear loading, SYS. So these values I can get by experiment. So once I get those values, I can decide whether the applied load or induced stress will cause failure of the material or not. If it is more than this value, failure will definitely occur. If it is less than this value, failure will never occur. First thing here. So in this case, we can easily say. So in tensile loading, I can say that for if it's aluminium material. So for aluminium, I will initially find out the value of strength in tension. So if the load is creating a stress more than that value, I will definitely directly say that it's going to fail. If the load is giving us a stress less than that value or the strength of the material, I will say that strength will failure would never occur. It's very easy to tell here. But when we are going with the combination of loading cases, that means here every case we are having either tension, compression or shear, but not the combination of them. For example, you are having a combination of the cases. So when you are having combinations here, the material experiencing tension, the material experiencing compression, also the material experiencing shear. So I took all the combinations here. You can go with the tension plus compression, compression plus shear. So shear plus compression like that. So you can take any combinations. So I took a general combination of all these 3 loading cases: tension, compression, shear here. So in this case, you can't decide. Just by having those values, you can't decide that the strength, that means the material will fail or not. Generally, you think that if strength and tension is some value and this tensile loading is less than that value, failure will not actually occur by tension. If compression loading is more than the compression strength, it will fail by compression. We can't take individual values. So generally, our mind will tend to think in that way, but actually it's not true. Because when combination loading cases are there, the way the metal is going to fail is depending upon the effect of all these loads. So we can't decide simply by taking strength in only one type of loading case. So to solve the problem or to decide whether the metal is going to be safe or not in these combination of loading cases, so we use theories of failure. So in general everyday life, everywhere, in most of the cases, we are having combination of loading cases only. Either tension plus compression, compression plus shear, or tension plus compression, or tension plus compression plus shear. So everywhere we are having this combination of loading cases only. So we need theories of failure to decide whether the loads are going to cause or create or keep the material under safer conditions or not. So if the loads are going to create failure, so then we don't go with those loads. So we'll go with the decrease in the magnitude of load or removing some of the loads, or we'll do some sort of arrangement or some sort of adjustment such that the loads are not going to create failure in these conditions. So to decide whether the loads going to create or the stresses induced are going to create or not going to keep the material safe or not, we have to use theories of failure. So I'll tell you the fund of the theories of failure here, or the basic principle by which we're going to decide. So we'll take the combination loading case, whatever we're going to deal with that. So for example, a general combination loading case is denoted like this. So tension one direction. So I'm taking tension other direction here. This might become compression also. And shearing is there in the other directions. So if you take a particular coordinate system, as this is x-axis and this has y-axis. So this is nothing but sigma x. This is nothing but tau xy. This is nothing but sigma y, tau yx, sigma y, tau yx, tau xy, and sigma x here. Okay, so we take that combination of loading case here. Before going further, I should give you the list of all the theories of failure we're going to study, or basically what are the theories of failure we should study for any competitive examination. So basically there are 5. I'm writing down here. The first one is maximum principal stress theory. Second one, maximum shear stress theory. And third one, maximum principal strain theory. And fourth one, strain energy theory. And fifth one is distortion energy theory. So these are all the theories of failure here, and they're all given the names based upon a parameter: maximum principal stress, maximum shear stress, maximum principal strain, strain energy, or distortion energy. So only the calculations will be different, because based upon the parameter, the calculations will be done according to that. But moreover, the concept is same itself. So I will take this explanation part with respect to this maximum principal stress theory, and then I will explain you these two theories of failure so that you can understand how we have to apply the concept and solve the numericals. So first of all, I'm going maximum principal stress theory here. In this one, the parameter is maximum principal stress. So for this loading case, based upon my strength of material concepts, I will find out the principal stress for this loading case here. So whatever will be our loading case, we can easily evaluate the value of sigma 1. So once you get sigma 1 here, so we have to compare the sigma 1 with the sigma 1 in uniaxial loading case. If there is sigma x in this x direction here, so sigma 1 of this case at the time of failure. There is a combination loading case here, and sigma 1 of uniaxial loading case. Sigma 1 of uniaxial case. It is sigma 1 of uniaxial case at failure. So this is sigma 1 of our combination loading case here. So the basic principle here is if our sigma 1 is less than this value, the metal going to be safe. Every theory of failure say in that way itself. For example, if it is maximum shear stress theory, so here you will be taking maximum shear stress, and here also we will be taking maximum shear stress of this case here, and we compare. So our parameter should always come less than this value here. Otherwise, you will be experiencing failure. Later we can check how authentic it is, and it is valid for our particular theory of failure is valid for how many types of materials. That thing we can decide. But basic principle of each and every theory is we have to find the parameter for our combination loading case and compare with uniaxial loading case at failure. If it is coming lesser than this value, the metal going to be safe. If it is not coming lesser, it's not going to safe. So this is, if this inequality is satisfied, it's going to be safe. If it is lesser, it's not going to be safe. It's not going to be safe at all. It's like this one here. So now, when as we are comparing with the uniaxial loading case, first of all we should know, or we should analyze this uniaxial loading case clearly. Then only we'll be able to understand how to relate with this value here. So first we should know these values, sigma 1 or tau max value or principal stress value or strain energy value, anything corresponding to uniaxial loading case here. So first of all, let's go with this uniaxial case. So I'm putting the title here. It's very simple here. If your metal is experiencing a tensile load in x direction, so it gives rise to tensile stress in x direction here. So if you write down the stress tensor matrix, it will be simply sigma x 0, 0 here. So for this case, if you find out, for this state of stress, if you are finding out principal stresses, sigma 1, sigma 2, and also maximum shear stress. So sigma 1 will come as sigma x, and sigma 2 will come as 0, and sigma tau max will come as sigma x by 2. You can check the calculations of that. So now, at the time of failure, so basically what happens is, sigma x can be any value here, but the metal can take sigma x value only up to yield point or ultimate point. It can't go beyond the strength of the material. So at failure, the sigma x actually reaches or tends to reach the value of SYT or SUT value there. So as sigma x is reaching SYT value, so at the time of failure, principal stress sigma 1 is equal to SYT, sigma 2 is equal to 0, and tau max value is equal to SYT by 2. You'll be getting the value like this. If it is a brittle metal, you'll be having SUT values here. This thing here. So you got all these parameters here. Now along with this uniaxial case, we should do the analysis of pure shear case also, so that we can see the authenticity of the each and every theory of failure in an experimental way. So which you will understand very thoroughly later. So we are going with analysis of pure shear case. Analysis of pure shear case. So pure shear case means that loading condition will be giving rise to only shear stresses 0, tau xy, tau ix and 0 here, and where the parameters tau xy, tau x both are same, so I'll denote it by tau itself. So for this loading case, if you're finding out principal stresses, sigma 1 is equal to tau, sigma 2 is equal to minus tau, and you'll be getting tau max value as tau itself. And this material also cannot take stress both more than the strength of the material in this loading case also. So at failure, this tau value reaches SYS or SUS. So yield stress and shear, ultimate stress and shear. So your principle is sigma 1 is equal to SYS, sigma 2 is equal to minus SYS, and tau max value is equal to SYS itself. So if it is a brittle metal, we'll be having SUS, minus SUS and SUS value. Okay. Now, before going into the first theory of failure or understanding the first theory of failure, we should have knowledge of assumptions we're going to take, or the main or important assumption we're going to take for each and every theory of failure. So assumption here is, so we take the magnitude of strength of the particular material in tension is equal to magnitude of strength in compression. Because generally what happens is, ductile materials are experimentally, it is proved that ductile metals are in general stronger in tension and weaker in compression. So the left parameter is higher and right parameter lesser for ductile materials. And for brittle materials, it is reverse. They are stronger in compression and weaker in tension. So we don't go with the inequality in the study of theories of failure. So we take assumption that magnitude of strength in tension is equal to magnitude of strength in compression. That's the thing which you're gonna take here. Now let's go with the first theory of failure here, the maximum principal stress theory. So from that we'll understand how to deal with each and every theory of failure. So I'm going with maximum principal stress theory here. So it's very simple theory here. So in fact, every theory of failure is very simple. After completing of understanding these two theories of failure, we get coming to that particular stage. So I said that what is the basic principle? So we take the maximum principal stress for our combination loading case here. So we have sigma x, we have sigma y, and also tau xy and tau yx. So we got these values here. So maximum principal stress theory. So for this one, we'll get the value of maximum principal stress sigma 1. We'll compare with the maximum principal stress of the same material in uniaxial loading case. So both the metals must be same. If it is aluminium, it should be aluminium. If it is copper, it should be copper. Otherwise, it doesn't make any sense. So we find out sigma 1 for uniaxial loading case at failure. So sigma 1 for uniaxial loading case at failure, if you turn your page and check it, you will be finding out that sigma 1 is sigma x in a general loading case, and sigma x value will reach at the time of failure as SYT value there. So sigma 1 is equal to SYT. So here it is SYT here. So this sigma 1 should be less than SYT for failure not to occur. If we need to go with the critical condition, then we need to take this as equal to here. We will take this one as equal to here. Now, sometimes instead of designing the material with respect to failure stress or the strength of the material, we will be designing with respect to allowable stress. But we know allowable stress is equal to, or we have factor of safety is equal to failure stress by allowable stress. That means allowable stress is equal to failure stress by factor of safety. So if you are taking factor of safety, instead of SYT value, which is nothing but failure stress, I will be putting allowable stress with this failure stress by factor of safety. So you will be having N in the denominator on the left side if you are taking the factor of safety value here. So this is the equation here. So you got the equation number 1 here. So remember, every theory of failure will be having two equations and a diagram that will help you to solve any question from any question of gate level or even IAS level or basic mechanical engineering papers levels there in most of the competitive examinations here. So now this theory is given like this, but we don't know how authentic it is. How authentic is the theory of failure here? So we should practical way or by experiment we should decide whether it is true or not, or it is valid for how many number of materials or which type of materials basically. So to do that, what we are going to do is I'm going to take an example of this particular loading case. I'm taking an example where sigma x is not there, sigma y is not there, sigma x is not there, sigma y is not there. I'm taking an example. If sigma x, sigma y are not there, only tau xy, tau yx are there, it's simply nothing but a pure shear case. I'm substituting sigma 1 for pure shear case. Sigma 1 for pure shear case is given by tau. At the time of failure, this tau becomes SYS value. So this becomes SYS, SYT. Generally, this SY is written on the left side. So this equation becomes SYS is equal to SYT. This is equation number 2. So this is an experimental value. This is an experimental value here. I can say that whatever the material is there, if it is going with these, it's actually satisfying this relation. That means I take some material. I take some material and do the tensile testing. I'll find out SYT value. And I'll take the same material and do the shear testing. I'll find out SYS value here. So if those magnitudes are coming as equal, then I can say that this theory of failure is valid only for that material, or for the materials which are actually satisfying the relation. If a material is giving you this value is half of this value, then it's not going to be satisfied there. So for experiment, it has been observed that out of the different types of materials which are present on Earth, they understood that this equation is being satisfied by brittle materials. So there is some sort of brittle materials. So this theory of failure is valid for. This theory of failure is actually valid for some sort of brittle materials. But because of its simplicity, this theory of failure is taken as valid for all the types of brittle materials there. So we are done with these two equations here. So if you apply the same concept in every theory of failure, you're going to derive equation number 1, equation number 2 here. So we need to know the region of safety also. So I will give you the derivation of region of safety for this theory of failure also here. So I'm drawing the region of safety now. Region of safety is nothing but we will draw a curve on a Cartesian system which is having sigma 1 axis as x-axis and sigma 2 as y-axis here. So we'll find out the region of safety here. So this region of safety will be having plots of sigma 1 comma sigma 2 here. So the sigma 1 sigma 2 values will be inside the region like this. So if your sigma 1 sigma 2 coordinates are coming inside this region, that means the metal going to be safe. That means here SYT greater than sigma 1. This equation is satisfied. This inequality is satisfied here. Okay, so this is denoted by these points here. If you are having SYT is less than sigma 1, so these are all denoted by other points here, which I'm denoting it by. That means it's not going to be safe here. So here it is safe, and here it's not going to be safe. So this is safe conditions, and this is not safe conditions. So for every theory of failure, this region curve will be going on changing. The equation of the curve will be going on changing for each and every theory of failure here. I will draw it for this theory of failure now. So our theory of failure is having equation number 1, which is basically given as SYT is equal to sigma 1. So this is a condition if sigma 1 is greater than sigma 2. If sigma 1 is greater than sigma 2 here. If your condition is sigma 2 is greater than sigma 2, sigma 2 greater than sigma 1, then your equation will become SYT is equal to sigma 2 here. Now if you take this 10 compressive loads, SYC is equal to sigma 1, SYC is equal to sigma 2. Now, you draw these 4 lines on a graph having sigma 1 and sigma 2. So, you take this one as SYT, SYC, SYT and SYC values, because anyways you know magnitude of this SYT and SYC values here. Now you draw these lines. First one I'm drawing here. SYT is equal to sigma 1. SYT is equal to sigma 1 means this is a line, vertical line. SYT is equal to sigma 2. SYC is equal to sigma 1. SYC is equal to sigma 2. So in this one you're gonna get sigma 1, sigma 2 values inside this region like this. So if these values are coming inside this region, this blue points, then the metal going to be safe. If they're coming outside this region, the metal not going to be safe. So you don't need to worry regarding the proof of this particular region of safety diagram here. But if you are just remembering the shape of the diagram, at least you'll be able to solve all the questions from previous GATE papers. So if you're preparing for GATE, just remember how the shape of the diagram is coming. So what's the shape of the diagram basically? So it's a square here. You just have to keep this in mind here. Now I'm applying the same concept to evaluate the expression or equations and diagrams for maximum shear stress theory. So the same way we'll do it for all theories of failure also. I'm doing it for maximum shear stress theory now. So let's go with the maximum shear stress theory. So for a maximum shear stress theory, it says that, so for our loading case, we need to get the value of maximum shear stress, sigma x, sigma y, this is tau x, y. So let's get the value of tau max here. Tau max is equal to given by, we can write down as tau max as sigma 1 minus sigma 2 by 2. For 2D state of stress, I'm first of all denoting it by 2D state here, where loads are acting in 2 directions. Tau max equals sigma 1 minus sigma 2 by 2. So we have to compare with the same material in uniaxial loading case. So in uniaxial loading case, you will be having tau max value at the time of failure as, so here tau max is equal to SYT by 2. So for your material to fail, your sigma 1 minus sigma 2 by 2 should at least becomes SYT by 2. Once this value reaches this value, failure will happen. Once this value is lesser than this value, the metal going to be safe. So if it is more than this value, automatically it's not going to be safe here. If you simplify this relation, you're going to get it as SYT is equal to sigma 1 minus sigma 2. This is equation number 1. Just like we got equation number 1 in the previous theory of failure, we are getting equation number 1 in this case here. SYT is equal to sigma 1 minus sigma 2. And if you are going with factor of safety, you will be having n here. Now to derive equation number 2, we have to substitute sigma 1, sigma 2 in terms of pure shear case. So sigma 1, sigma 2 in pure shear case is nothing but sigma 1 is SYS and sigma 2 is minus SYS is equal to SYT. If you simplify this, this will become SYS is equal to 0.5 SYT. It is equation number 2. In the earlier theory of failure, we got SYS is equal to SYT, but here it is 0.5 SYT here. And this equation is actually satisfied by the ductile metals only. So it's valid for only ductile materials. So it's like this, we have to derive equation number 1, equation number 2 in this way, and we have to do the calculation. Now if you are going with the region of safety, so region of safety, to draw the region of safety we need equation number 1, SYT is equal to sigma 1 minus sigma 2. Anyways, we are drawing the graph between only sigma 1 and sigma 2. We are not concerned regarding this particular sigma 3. So we are concerned regarding that one itself. So if sigma 1 minus sigma 2 is there, if sigma 1 is greater than sigma 2, and SYT is equal to sigma 2 minus sigma 1 if sigma 2 is greater than sigma 1 here. And also if you take 3D state of stress, so what happens is, in a 3D state of stress, your equation number 1 will change, because your maximum shear stress will be maximum of sigma 1 minus sigma 2 by 2, comma sigma 2 minus sigma 3 by 2, comma sigma 1 minus sigma 3 by 2. It's equation. So this should be equal to maximum shear stress in uniaxial case, SYT by 2 here. So this equation will be this maximum of sigma 1 minus sigma 2, comma sigma 2 minus sigma 3, comma sigma 1 minus sigma 3. So anyways, if you take sigma 1 is highest value, sigma 2 is intermediate value, and sigma 3 is the least value, you will be taking this is the highest value in this out of these 3 values here. But anyways, just write down this way here. So you'll be getting the answer according to this one here. So SYT is equal to sigma 1 minus sigma 2, sigma 2 minus sigma 3, if it is a 2D state of stress condition here. If it becomes 3D, whichever the highest value will come. So you can have a chance of sigma 1 minus sigma 3, sigma 2 minus sigma 3 also. But anyways, in this graph, we are not plotting according to sigma 3 dimension. Because if you are plotting sigma 3 dimension also, then it will become a volume, say a region of, not the region of safety, it becomes a volume of safety there. So sigma 3 will be neglecting here. So your other two equations will become SYT is equal to sigma 2, SYT is equal to sigma 1. These are the equations here. I'm writing this equation here. Just keep in mind that for a 3D state of stress, this is the equation number 1. So for 3D state of stress, this will become the equation number 1. So whenever question comes, you just have to identify whether it is a 2D state of stress or 3D state of stress. Otherwise, if you are going calculations of 3D state of stress for the 2D state of stress or vice versa, you'll be ending up getting wrong answer. Many previous gate questions are there which are given in the way itself. So you should be able to identify whether it is 2D or 3D and apply the correct formula. So if it is 3D, go with this formula. If it is 2D, you go with the earlier formula there. So you got these equations here. These are all the things here. Now, if you take down or if you plot down these 4 equations, basically SYT, SYC, SYT and SYC. So anyways, whatever the 4 equations we took, these are there here, because here sigma 1, sigma 2 are there. If you take in compression, SYC is equal to sigma 2, SYC is equal to sigma 1. So these 4 lines I have already drawn in the previous theory of failure. So they are nothing but vertical and horizontal lines passing through SYT and SYC here. Now if I want to plot these first 2 equations, they are actually these 2 lines here. So the actual region of safety is nothing but hexagon here. So if they are coming inside this region, the metal going to be safe. If they are coming, sigma 1, sigma 2 values are coming outside this region, the material not going to be safe. Sigma 1, sigma 2 values are coming out of the region, the metal not going to be safe. So just I'm applying the same concept again and again and deriving equation number 1, equation number 2 and regional safety and getting the answers here. So you take any question from previous gate papers, so you just have to evaluate whether the factor of safety, you just have to evaluate the value of SYT value just by using equations 1 and equation 2. Or you will be having questions which are on matching, where you have to match the name of the theory of failure with the regional safety diagram. So that's a way in which you have to do it here. So there is very easy. That means this concept, these theories of failure concept is very easy to get the marks. That means mainly for mechanical engineering people, you are having one question compulsory every year on theories of failure. So if you are going with understanding of theories of failure in this way, it becomes very easy for you people to solve the questions and get the answer at any cost. So I advise you all to go with these things, and based upon that you can derive the equations or equation 1 and 2 for other theories of failures also, you can do it. Thank you so much. All the best.